mathematics and computation. He is also the editor of Ecological Complexity, Theoretical and Mathematical Ecology section of the journal Mathematics. And one more statement, he is a batchmate of myself and he is one of the brilliant students of our batch. Now, I would like to request Dr. Malay Banerjee to deliver his lecture. Over to you, Malay.
Thank you, Nasima. So first, let me share my screen. Can you see my screen?
Yes, it is visible.
Okay. Thank you very much for your kind invitation and as well as kind introduction. And before going to talk about my today's topic, that is Legendre Equation, I must say that today is a very mixed experience for me because Nashima invited me, who was my batchmate. And while I was looking at the list of participants who are attending, I can see some of them was my senior in the Department of Applied Mathematics when we are involved with the MSc courses, and sometimes I ask them that which book should I consult for this topic, and this is a little bit challenging and embarrassing to deliver talk in front of them. And also I can see another participant from whom I have learned a couple of mathematics when I was at +2 level and BSc level. Okay, thank you very much once again for your kind invitation and introduction. So let us start with today's topic, that is Legendre Equation and Legendre Polynomial, derivation and application. At the very beginning, I must mention that this is a very broad topic, and due to some urgent work and mainly to make some arrangement at our home site, because from today again lockdown has been started here. So from yesterday night up to tomorrow morning there is a complete lockdown, and that's why I completed preparing my slide just 15 minutes back to the commencement of this event. So let me talk about something which is related to Legendre polynomial. So before going to Legendre polynomial, first I want to give you a quick example just to understand that why or how series solution is important and interesting for practical application. Most of the time, what I have done during my college life, university life, and even research until today, I just want to understand each and every theory with some practical examples. In case of abstract mathematical theory, if I cannot visualize the result, then sometimes it poses some difficulty in front of me that what is going on there. So my today's task is to give you some sort of idea such that you can visualize what is going on in order to understand what is Legendre equation, what is Legendre polynomial, what is solution, what is series solution, etc., etc. So the first question, you might be surprising that this is a very simple equation. Why I am interested to solve it in terms of series solution? Answer is that I just want to show you that whatever solution you will get explicitly by solving this equation directly with the help of your knowledge at your +2 level, same solution can be retrieved by the method of series solution. Then the question is that then what is the utility of series solution? Utility is that there are plenty of equations for which you cannot find out any closed form solution, and those equations can be solved with the method of series solution. So if you solve this equation directly, you can find this as the explicit solution. Keep in mind, it provides you a family of solution. In order to have just unique solution, you need to impose some initial condition. If you look at the expansion of e to the power x squared, so you can see this is the series expansion of this solution. So now the question is that if we start with a standard assumption for existence of a power series as a solution of this problem, then whether we will get back this solution or not. In this case, answer is yes, because equation is well behaved. There is no singular point, and we can assume a solution of this equation in this particular form because x equal to 0 is an ordinary point. It is not a singular point. So we don't need Frobenius series solution. We can find out a power series solution in this particular format. Now, once you need to work with this kind of series and using them to find out the solution of this ordinary differential equation, you need to be familiar with the differentiation of this series term by term and their expression in terms of m, which is most important. If you are able to understand the notation of derivative of y with respect to x and its representation in terms of m appropriately, and then if you do some boring algebra just by substituting this equation into the given differential equation, and if you equate the like powers, that means equating the coefficient of like powers, you will find the desired solution. Now the point is that first of all, if we calculate y dot x, then you will find this one. Now just to give you some sort of new essence, that I am differentiating this series. So it is known that when x to the power n is differentiated with respect to x, its index reduces to m minus 1. But maybe I am a stupid person, that's why I have written here x to the power m again. But the point is that keep in mind, in both these cases, the range of m is from 0 to infinity here, as well as it is 0 to infinity at this place. And the point is that now I will explain from here, if we consider the first derivative with respect to x, then how you can arrive at this particular expression. Maybe you are well known with this notation, but just for my convenience, I want to say a few words about this part. So to justify what we can do, we can write down this series explicitly, and then if we differentiate term by term, assuming this differentiation is allowed, so that means uniform convergence of the series over the certain domain of definition is assumed. So then you can find y dashed x is equal to a1 from this term, then 2a2x from second term, then a3x cube as the third term, and so on. And in general, it is written in this particular format. So the point is that if you write this step from this one, keep in mind that this gives your clear-cut understanding, that is m a to the power m x to the power m minus 1. But don't forget to change m from 0 to m equal to 1. If you keep m equal to 0 here, this will start from a term x to the power minus 1, which you cannot find out by differentiating this series. So that's why this is a point of caution. Now what you can do, you have this expression as y dot x, then you replace m by p plus 1. So in this particular part, you have thoroughly replaced m by p plus 1. So as a result, m minus 1 becomes p. But keep in mind, here the range of summation was from m equal to 1 to infinity. You are not allowed to this range, and therefore as m equal to p plus 1, so you need to consider this summation from p equal to 0 to p equal to infinity. And now what you can just check, you can check that the term p equal to 0 corresponds to this term m equal to 1, then p equal to 1 corresponds to the term p m equal to 2, and so on. And now p is your dummy index at this stage, and again you can change it to m in order to find out this expression. So this one I have written earlier directly. And keep in mind, this kind of practice can be followed for any higher order derivatives of yx with respect to the variable x. Now, if we substitute these two expressions, that is yx equal to this one, and finally y dot x equal to this expression into the given equation, then you can find this relation, I must say this relation. And the point is that if we assume that y equal to summation a to am x to the power m is going to be a solution of the given equation, then it should become an identity for all values of x. And now taking x inside the summation sign, you can rewrite this expression like 2am x to the power m plus 1. So once it is an identity for all real values of x, so what you can do, you can just collect the coefficient of like powers of x from both sides in order to find out the unknown quantities a0, a1, a2, a3, and so on. If you try to do that, so this is an identity, if you try to do that, so explicitly you can write this expression, and on the left hand side there is a constant term, on the right hand side there is no constant term, rather it is starting from the term x. So then step by step, equating the coefficient of like powers from both sides, you will get a1 equal to 0, 2a2 equal to 2a0, then 3a3 equal to 2a1, and so on. You will get this kind of equations. Now the point is that this step clearly gives you a1 equal to 0, and all these results, that means 2a2 equal to 2a0, 3a3 equal to 2a1, and so on, can be written simply in a combined form, that is m plus 1 a m plus 1 equal to 2 a m minus 1. This is valid for m equal to 1, 2, 3, and so on. And with the use of a1 equal to 0, so what you can find a3, a5, a7, all of them are exactly equal to 0. And therefore, you will have this one. And then if you start solving a3, a5, etc., then a1 remains unknown. So ultimately, you will find that a2 equal to a0, a4 equal to a0 by 2, a6 equal to a0 by 3, and so on. And ultimately, now if you substitute these values, that is a1, a3, a5, a7 are 0, and this a4, a6, a2 in terms of a0, then you can find yx equal to this one, and this will give you a0 equal to this one. So just try to accept the fact that not only you get back the actual solution what you have obtained very easily, again with the method of series solution, and also you have this only one free parameter in your hand, which is the arbitrary constant, which is involved with the solution of the first order differential equation. And the question is that why we are interested for this kind of series solution, how it relates with the actual solution. Here, just as an illustrative example, I have plotted some of the functions. So this red dashed color curve is for 1 plus x square. Then yellow dashed color curve for 1 plus x square minus x plus x to the power 4 by factorial 2. Then this this violet color curve, or maybe you can say brown color curve, is for the term up to x to the power 6. And finally, this blue color solid line is for exponential x square. And the point is that what you can observe, that if you move away from the value x equal to 0, so then the convergence of the function with respect to these approximated solutions started increasing, and then we need to understand at a particular value if we want to judge the solution from the series of the given equation, that means series solution of the given equation, you need to find out some way out to decide how many terms is required to be considered in the series expansion in order to have a good match of the system. But on the other hand, what I try to explain here, or before going to Legendre polynomial, why I'm considering this problem, this is considering this problem only for the reason that this 1x, x square, x cube, x to the power 4 and so on, if you have this collection of monomials and if you adjust them with appropriate constant, that means multiply and add or subtract, then their summation is going to be a solution of the given problem. So what we can say that 1 plus x square is an approximation of the original solution. Then 1 plus x square plus x to the power 4 by factorial 2. This is a little bit betterment of the solution. So once we are adding more term into the series, so we are getting some better approximation of the solution, which is very much clear from this particular picture. Now you may ask the question, what is the relation of this concept with the Legendre equation? Okay, let me first introduce the Legendre equation, and towards the end of the talk, I'll show you what is the relation or why I am interested with this kind of representation. So, okay, Legendre equation in general is defined in this particular way. So once we define this equation as a Legendre equation, two natural questions arises. Number one, what is the range of x and what is lambda? Clear-cut answer to these questions are lambda is a real number in general, but precisely within this talk, I will consider lambda only as positive integers, and also x for Legendre equation belongs to the bounded domain -1 to +1. So these two things are mentioned here, and for the time being we can consider just lambda is a real number and x belongs to -1 to +1. So this is some sort of restriction, or maybe you can say we can derive this restriction from the convergence of the series which are going to be the solution of this kind of equation. So this equation can be written explicitly in this particular format. So that means in the form of a0x d2y dx2 plus a1x dy dx plus a2xy equal to 0. But this form sometimes well known and is more frequently used in higher mathematics because it is the equation which is written as a Sturm-Liouville problem. And this equation again can be rewritten in this particular format in order to ensure that this equation possesses some singularity, that is at x equal to 1 and x equal to -1. But fortunately, this equation is well behaved near origin, because x equal to 0 is an ordinary point, not a singular point for this equation. And most popular form of the Legendre equation that you can find in most of the books, that is in this particular format, where lambda is given by n into n plus 1, where n is any non-negative integers. So that means n is any natural number or it is equal to 0. Within this lecture, I will concentrate for lambda with this particular restriction, that is n belongs to this set. Now let us try to find out the solution of the Legendre equation by the method of power series expansion. So we assume yx into this particular format. Proceeding in a similar way as earlier, we can write y dot equal to this one and y double dot is equal to this one. I hope the way I have explained, you can also derive this expression in terms of y double dot x. Now with the reference to Legendre equation, y double dot x is equal to this one, because now I am going to consider what are the different terms in terms of the series which are involved with the Legendre equation. So first term is y double dot x. Second term minus x square y double dot x. So you can take this x square within the summation sign. So there will be some sort of alteration at this particular term, but no change in the range of values of m. Then from the second term of the given differential equation, you will find this third term, that is minus 2xy dot x. This will comes out to be this expression. And finally, n into n plus 1 yx, this is equal to this one. And now what we can do, either who are at the entry level, they can start with collecting the lowest power of x. And if you are expert, that means after having some experience in this particular area, I just want to say that you have to be very much careful such that you should not miss any one of these terms. But the best possible way is that I'm going to show you. You just practice some of the problem in this particular way, and then you can write down the solution directly from this equation by deriving the recurrence relation in order to find out the complete solution of the problem. So what you can consider just as an expansion of this all series and put them in a tabular form. So this is the tabular form. So from y double dot x, we just collect the coefficient of x to the power 0, that is constant term x, x square, x cube, and then you write down the coefficient of general term, that is x to the power m. So if you do this practice for all the terms, that is y double dot x, then minus x square y double dot x, minus 2xy dot x, etc., etc., you can prepare a table like this. So what will happen, simply in order to equate the coefficient of x to the power 0, you just need to consider sum of all these terms in this row, that is equal to 0. Similarly, coefficient of x to the power 1 equal to 0 is the sum of the elements in the second row is equal to 0, and so on. And finally, if we consider the last row, then you will find the general recurrence relation. But the point is that this table gives you lots of different information. What are first two prominent informations are that this kind of result is valid for the coefficient of x square and onwards, that means x square, x cube, and so on. And coefficient of x to the power 0 and coefficient of x to the power 1 are not valid or cannot be derived from this expression, because some of the term might be absent, and which are absent here you can clearly visualize. So that's why you write down these two equations separately, and then in general you can write this expression, and from where you can construct the recurrence relation. If you do that, then what will happen? You can find a2 equal to this one. That means first row, if you add the elements and equate to 0, then you can find a2 in terms of a0. Then from the second one, you can find a3 in terms of a1. And then from the third one, you can calculate a4. But in general, from this one, you can derive am plus 2 in terms of am. So why I encourage to write you this couple of initial iterates, just you can verify that a2 is represented in terms of a0, a3 is represented in terms of a1, a4 is represented in terms of a2, and this suggests am plus 2 can be written in terms of am. And finally, if you do that, then you can find am plus 2 is equal to this one, where m starts from 0, 1, 2, and so on. So if you start substituting here, you can verify the quantity a2 and onwards. So from this relation, you can calculate a2, a3, a4, a5, a6, and so on. But two quantities remains unknown, that is a0 and a1, and you should be very much happy about that, because we are solving a second order linear ordinary differential equation. So its solution must be linear combination of two linearly independent solutions, and where the linear combination has to be taken with respect to two arbitrary constants, and here a0 and a1 will play the role of that arbitrary constants. So if you can derive, so a with even suffixes, those will run like a2 equal to this one, a4, from this relation you can write this multiple of a2, and then back substituting the expression of a2 here, you can find out finally A4 in terms of A0. Similarly, you can calculate A6 in terms of A0 and so on. So I have written this expression in a specific way such that you can understand that I am starting from n minus 4, keep on increasing with plus 2 and stop at n. Then start from n plus 1, go up to n plus 5, and this 5 is related to 6, just 6 minus 1, and this is related with the fact this is 6 minus 2, and so on. Similarly, from this relation, if you start with A1, then you can find A3 in terms of A1, A5 in terms of A1, and A7 in terms of A1, and so on. And now if you club all these results together, then you can find Yx. This is a general solution to the given equation, which is a linear combination of y1x and y2x, where y1x is given by this one and y2x is given by this one. So these are two solutions. And you can verify that these are two linearly independent solutions. And simple understanding is that you cannot find out two scalars such that when y1 is multiplied by alpha and y2 is multiplied by beta, and after addition they will be equal to 0 for all values of x, and such that alpha beta not equal to 0. This is more or less absurd. Just by collecting the coefficient of constant term and coefficient of x, you can prove alpha beta is equal to 0. So this means these two solutions are linearly independent. But some special cases from here that we can derive, because already I have mentioned that n belongs to 0, 1, 2, and so on in that particular set. So that means set of non-negative integers. So as a special case, what I can going to show you here, that if I step by step choose n equal to 0, 1, 2, and so on, what is going to happen? For n equal to 0, from first expression, you can find only one term, that is 1, and rest of the term will be absent because in all this term, n is explicitly present in the numerator. So you will find only one term as a solution, but this will give you an infinite series solution, that is y2x is equal to this one. Now, if you consider n equal to 1, then y1x is an infinite series, but y2x, this is a terminating series, rather it is a first degree polynomial. Similarly, if you substitute n equal to 2, you can find y1 is a polynomial solution and y2x, this is a series solution. And just for any non-negative integers, what is the take-home message from here? I am not going to any complicated situation. Just from this expression and this explicit expression that you can see from here, with the help of recurrence relation, we can understand for all non-negative integral values of n, for each of them, you will find a polynomial solution and an series solution. So this is one important message that we can take forward from this particular step. So now we try to understand few more properties of the solutions. So the point is that I have mentioned earlier, that when n belongs to this set, there always exists a polynomial solution. And also there exists a series solution which will converge whenever x square is less than 1. Alternatively, we can say modulus x less than 1. And this convergence condition you can derive by applying the ratio test. Now for n equal to 0, you will have y2x is equal to this one as a solution. But the point is that what is going to happen if x square is equal to 1? If x square equal to 1, you can verify that this series is either this one itself, that means in case x equal to 1, or it will be minus 1 multiplied by this series in case x equal to minus 1. But the point is that you know that this is a divergent series. So that means this solution, that is infinite series solution y2x, it does not converge for x square equal to plus minus 1. But for application purpose, what we need a solution which converges for all x lying between minus 1 and plus 1. So from where we will get that kind of solution? We'll get that kind of solution just from the polynomial solution. And that's why, in order to make our life simple, in the title of my talk, I have given Legendre equation and Legendre polynomials. We are not going to consider these kind of things in any detail, but towards the end, I'll give you a couple of examples that how these kind of solutions looks like Legendre polynomial. So Legendre polynomials are the polynomial solution of Legendre equation with some additional property, and also Legendre functions are the series solution of the Legendre equation. Those are called Legendre function. And finally, what I like to mention here, that solution of the equations for negative integral n, that most of the time people overlooks, because all the solutions for negative integral n can be obtained from the solution of Legendre equation for non-negative integral n. Just for your quick verification, you can try to verify that in case n equal to -2, the Legendre polynomial will be y2x is equal to x, which corresponds to actually the Legendre polynomial of degree 1. Keep in mind, as of now, I have not defined what is Legendre polynomial. So now we can define what is Legendre polynomial. Legendre polynomial is a polynomial solution of the Legendre's equation and satisfies the condition y1 equal to 1. And this is known as Legendre polynomial. And in most of the book, you can find, in general, it is denoted by Pnx. Why it is denoted as Pnx? Because n determines, the value of n determines the degree of the polynomial. And as it is a polynomial solution having some specific property, so that means some sort of higher level element of polynomials, which are in general denoted by small p suffix nx. So therefore, Legendre polynomial is capital P suffix nx. And what are the Legendre function? A series solution of the Legendre equation which converges for q square less than 1 is called Legendre function. And in general, Legendre function of order n is denoted by qnx. And some of the references you can find Pnx as a Legendre function of first kind and qnx as Legendre function of second kind. This first kind and second kind only based upon the fact that this Legendre function of first kind is convergent, but this is not convergent at the end point. So that's why we need to classify them as first kind and second kind. Now, what are the properties of Legendre polynomials? So just try to understand, and we can derive what are the Legendre polynomials are. For n equal to 0, we have y1x equal to 1. So then the solution will be yx equal to a0 y1x. So why we are not going to consider a1 part? Because we need the polynomial solution. We are not interested for series solution. And we know at x equal to 1, series solution does not converges. So in order to have a well-behaved solution, that is, in order to apply the condition y1 equal to 1, we are forced to choose a1 equal to 0, and this gives a0 equal to 1. And as a result, you can find p0x is equal to 1. Similarly, for n equal to 1, using the similar kind of argument, you can find p1x equal to x. Then for n equal to 2, again applying this result, you can find p2x equal to this one, and so on. And if you keep on proceeding, that means from series, if you evaluate all of the functions and then use the condition y1 equal to 1, then you can derive these are the first 5 Legendre polynomials. Now the question is that all the time these are this much boring to do some calculation from extraction of the series and etc. Answer is no. There are several other methods by which you can show this, or you can derive this kind of Legendre polynomial, and that is the main focus for my talk in the remaining part of this today's lecture. Okay, so these are some plots of the Legendre polynomial. This is p0x, this blue line. Then red line is the p1x. Then yellow one is p2x. then this violet color one is P3x, and green one is P4x. And now you can see that all the curves, they passes through the point 1, 1, and that's why in case of Legendre polynomial we have imposed that condition. On the other hand, you can have a quick observation that P0, P2, P4 at x equal to -1, they are +1, and P1 and P3 at x equal to -1, this is actually -1. So the point is that what you can think about that P0x, P2x and P4x, that means all P with suffix even integral in x, they are solution of Legendre equation satisfying the separated boundary conditions, that is x at x equal to -1 it is 1, as well as at x equal to +1 it is 1. And on the other hand, for odd polynomials, that is P1, P3, they satisfies a different boundary condition at x equal to -1, and that is why at x equal to -1 is -1 for the odd Legendre polynomials. Of course, we can derive these properties from other results also. So one interesting formula that is involved with Legendre polynomial is the Rodrigues formula, and it says that from here you can derive the Legendre polynomials for n equal to 0, 1, 2 and so on. But the first what we need to see, we need to prove that this is a Legendre polynomial. So that means it satisfies the Legendre equation, and also it satisfies the condition that is at x equal to 1, this should be equal to 1. So in order to do so, what we can consider Vx equal to this one. Differentiating V once with respect to x, and after some simple algebra, you can calculate, you can derive this equation, and then if you differentiate both sides n plus 1 times with respect to x and with the help of Leibniz rule and make some arrangement of the terms, then you will arrive at this kind of equation. And here Vnx actually stands for nth derivative of v with respect to x. So now if you consider Vnx as a function, say gx, you can clearly understand that gx satisfies the Legendre equation. So what we can say? We can say that Pnx, that is Legendre polynomial, is a scalar multiple of Vnx, and we need to find out this alpha. From where we can find out this alpha? Using the condition Pn1 is equal to 1. If you substitute x equal to 1 here, so Pn1 equal to 1 will give us the alpha. But in order to find it out, what we can do, we can write this expression in a clever way, that is x plus 1 whole to the power n multiplied by x minus 1 whole to the power n, and then we can differentiate it n times with respect to x. And if we consider this as a first function u and this as a first function v, not this capital V, rather small v, and then apply Leibniz formula, then first term will be this one, and second and all other remaining terms will contain x minus 1. So why I am interested in this particular format? I am interested in this particular format only for the reason that apart from this term, rest of the term will be exactly equal to 0 if you substitute x equal to 1. And as a result, once you substitute x equal to 1, so then you can find that alpha factorial n, then 1 plus 1 whole to the power n, this is equal to 1, because this is your Vn and this is your alpha Vn at x equal to 1. This is required to be equal to 1, and which gives alpha equal to 1 by 2 to the power n factorial n. So now if you combine these three results, that is Vx equal to this one, Vnx satisfies Legendre equation, and alpha equal to this one, then you can prove the Rodrigues formula. Now, what are the other quick properties? Other quick properties of Legendre polynomials is that Pn minus x is equal to minus 1 whole to the power n Pnx. And just believe me, this proof is completely based upon an observation. What is observation? Observation is that Pnx containing only even powers of x if n is even, and Pn, it contains only odd powers of x if n is odd. Just from this property, you can say Pn minus x is equal to minus 1 whole to the power n Pnx. And again, from here, what you can obtain, if you substitute x equal to 1 here, so Pn minus 1 is equal to this one, and that you have observed in that picture that in case of n is even non-negative integer, this is 1, and for odd positive integer, this is equal to minus 1. Also, you can prove that for m not equal to n, keep in mind this m is not involved with the that means dummy variable in the series. Now we are completely within the Legendre polynomial. So we are talking about two non-negative integers m and n. And it says that if m and n are two unequal non-negative integers, then it implies that two Legendre polynomials of degree m and n, they are orthogonal to each other. Now, how to prove this result? At a first glance, it might seems to you that it might be very difficult and lengthy proof to ultimately arrive at here, because just we have seen the Rodrigues formula, we have seen some of the expression for Legendre polynomial. Then proof of this result will be quite involved. But believe me, it is very straightforward and little bit tricky. What is the trick? Pmx, that is Legendre polynomial of degree m, it satisfies this equation, and Pnx, that is Legendre polynomial of degree n, satisfies this equation. Now what you can do, you can multiply first equation by Pn and second equation by Pm, and then subtract, and after some clever arrangement of the term, what you can obtain, you can obtain ddx of this expression is equal to this one. Now, in order to do that, what you need to do, in both the part, you need to introduce, that means after multiplying first one by Pnx, then second one by Pmx, and after subtraction, then you need to add and subtract the same term, that is 1 minus x square Pm dash x and Pn dash x. Just with the help of simple observation, you can put the equation in this particular format, or directly you consider this equation in the form 1 minus x square Pm dash x and this as Pn dash x as product of two function, and apply ddx of u into v, you will immediately arrive this part of the equation with the added term as I have mentioned just now. But the point is that after integration, what will happen? This will give you integral of this pre-multiplied by this constant, but on the left hand side, this will be just this expression because it is a complete derivative. And once you integrate it, and from the limit -1 to +1, what will be the contribution from the left side? Contribution from the left side will be exactly equal to 0. Why? Because 1 minus x squared at x equal to +1 and x equal to -1 is equal to 0. And we know that m and n are non-negative integers. They are unequal. So neither n minus m is 0 nor m plus n plus 1 equal to 0. So we are left with only one option, that is integral -1 to +1 Pmx Pnx dx. This is equal to 0. But now I must make one statement for the student participants. This is not my credit that I have given you a very simple proof. Rather, it is a general property of Sturm-Liouville boundary value problem. I don't know, I did not get enough time to talk with Nashima or to look at your syllabus in detail. That is whether the Sturm-Liouville kind of boundary value problem is already covered in your syllabus or not. If it is done, that means, or if you are interested, you can have a look at this. Then most of the properties of Legendre polynomials can be obtained very easily. And secondly, what you can prove that if Pm is replaced by Pn, then it will give you this one. So ultimately,